simple Brayton cycle with air as a working fluid, which has a pressure ratio of 12, okay? So it's the same thing as the volume ratio we just saw, but in this case, it's the pressure ratio, okay? So maximum pressure over the minimum pressure is 12. It has a maximum cycle temperature of 600 Celsius and operates the compressor inlet at 100 kilopascals, 50 Celsius. Which will have the greatest impact on the backwork ratio, the compressor isentropic efficiency of 80 or a turbine isentropic efficiency of 80? Use constant specific heats at room temperature, okay? So once again, we can use those relationships for the isentropic transformations. We can use the K, you can use CP and CV. This makes our life so much easier, okay? But before we go back to the question, this is just a drawing of what's going on, right? We have our state 1 before the compressor inlets, then we compress the air, and then we're gonna, is it air? Air, yeah. And then we're gonna add the, we're gonna have the combustion happening here due to the addition of fuel and explosion. This is gonna expand and turn this turbine, and then we're gonna have the heat rejection going from 4 to 1 over here. And before I go back, I just wanna make sure that you guys understand the question, okay? Because this is not a trivial question. This is asking the following. Suppose that I have a completely reversible turbine, okay? So it's an isentropic turbine, but a compressor that only has 80% efficiency. And let's compare that to the inverse. That is, a compressor that's 100% isentropic, or that means reversible work, right? It's completely reversible, and a turbine that only has 80% efficiency. And which of these is going to have the greatest impact on the backwork ratio? So what is the backwork ratio? Hopefully you guys learned that through the lectures, so I don't have to go over it. Since I don't know that's usually not the case, let's talk about it quickly. Brayton cycle. So the Brayton cycle is the one that has very similar to the diesel one, but instead of having only one isobaric, we're going to have two isobarics. So one isobaric here, one isobaric here. And then we have, again, isentropic compression and isentropic expansion. 1, 2, 3, 4. Once again, going on the clockwise direction. Okay, and on this problem, this is where we introduce the next graph we can use. I'm going to draw this in the bottom here, which is a TS diagram. TS diagram, no, as you expect, this is temperature versus entropy, okay? And we can think about it quickly. Check it out. If the compression from 1 to 2 is an isentropic process, my entropy does not change, right? So I have to go straight up. So, boom, here you go, from 1 to 2. Okay, then I have a heat addition in which my volume is going to change and my entropy also changes. It's isentropic. So I have to go up here. So my temperature and my entropy will change. Boom. Then I have another isentropic one, which is an expansion. So I can go straight down with no change in entropy. And then finally I finish it off with the heat rejection over here. So it's the exact same thing shown in respect to different properties. Okay? TS diagram is going to start showing up a lot as well from this point onwards. Okay, now backwork ratio. Backwork ratio, I'll denote that as a BW, okay? And the backwork ratio is simply the work of the compressor over the work of the turbine. Okay, so in other words, for the compressor to be able to compress the fluid, we need to give him some work, right? So there's some work coming in here. And then when the turbine outputs the work, it's outputting over here, right? So that's what happens in the cycle. Now, the less I need to give to my compressor and the more I can get out of this turbine, the better my system will be, right? Because they're getting more useful energy out of it. So the smaller my backwork ratio, the better. Okay, so what are we trying to do? We're trying to compare the backwork ratio of a system that has an isentropic compressor and an isentropic compression in a normal turbine, and one that has a normal compressor and an isentropic turbine. Once again, I can use my CPs and my CVs, take them as constants. So that means that I can use my relationship C2 over C1 equals P2 over P1, K minus 1 over K. Okay, this relationship here is exactly the same as the one before that we did. T1 V1 to the K minus 1 equals T2 V2 to the K minus 1, right? The only difference is that I'm subbing in P instead of V using PV equals nRT. So I'm subbing in P1, P1, T1 equals P2, P2, T2. You guys can do that on your own afterwards. So just take the previous equation and just sub where you have volume sub the others. Other things are going to end up here. What do we have? We have the inlet of the compressor is 100 kilopascals. We have the temperature of the inlet is 15 Celsius. That's 288 Kelvin. And it also says the maximum temperature is 600 Celsius. Okay, so what is the maximum temperature? On the TS diagram, it's easier to see. Right, just by looking at the TS diagram, what's the maximum temperature we're going to have in this cycle?
H3.
3. There, right on. Right, so T3 is 600 Celsius, which is 873 Kelvin. Okay, that's the information we have to start with. So this problem, it's kind of hard. It's very hard for me to explain in a way that doesn't get you guys confused. I'll do my best. Stop me if you have trouble, okay? We have K and we have CP from the start. Don't forget K for room temperature is 1.4, and CP again from table A2, right? Just like on the first problem we solved today. And the CP from the same table is 1.005 kilojoules kilograms Kelvin. Okay, informations that we have to start with. So what I'm going to have to do is I'm going to have to calculate the work for the compressor, if it's isentropic compressor, and the work for the normal turbine, and also the work for the actual compressor and the isentropic turbine. Okay, so that's a lot of little things we need to calculate. And the way I'm going to do it is I'm going to do the following. I'm going to calculate what is the theory value for T2. Because when we go from 1 to 2, okay, if my compressor does reversible work, I'm going to end up in a certain temperature. But if my compressor has irreversibilities, it's going to end up in a higher temperature. And we want it to stop at the minimum temperature possible, right? And then I'm just going to relate this equation here. My T2 should be equal to my T1, P2 over P1, K minus 1 over K. T1 we have, P2 over P1 we have as well, because we have the pressure ratio. I forgot to write it down, but we do have it. I think it's 12. Yeah, 12. Okay, so it's right here on the corner. P max over P min is 12, and that's equal to which pressures? What's the maximum pressure on my system? Which states?
2 and 3.
2 and 3. 2 or 3, right? I'm going to put a little comma there. Make sure that you guys don't get confused. And then the minimum one, 1 or 4, and they're the same. Yeah? So there you go. So 2 over 1, that's 12. So this is going to be 12. This is 1.4. I have everything I need. So 2 equals 288, 12, 0.4 divided by 1.4. So 2 is 585.77 Kelvin. Okay, so this is what happens in theory. In practice, however, if this compressor here is only 80% efficient, what does that mean? Well, if you guys recall, the efficiency of a compressor, the isentropic efficiency of a compressor, will be the work that requires for the ideal case, isentropic one, divided by the work of the actual case. Okay, and if it's a turbine, it's the other way around. Remember, it's a turbine, so let's put C here for compressor and T for turbine. It's turbine, it's going to be the actual one, because it's always going to be smaller than the isentropic one over the ideal one. Okay, and this, hopefully this is intuitive for you guys too. We want the minimum possible, right? So the actual one is always going to be greater than the ideal one. And a turbine will in the maximum possible, so the actual is always going to be smaller than the ideal one. So let's calculate the actual. I'll put T2A for actual. What is the actual temperature that we end up with? And mind you that, as I said, it should be something greater than 585, which is not something that we are particularly looking forward to, but we know it's going to happen. So if we go to find this work here, from 1 to 2, what we can do is do the difference in enthalpy, right? So we did that before in the past too. That's going to be the enthalpy of from 2 to 1, so that's going to be temp enthalpy of the ideal one minus the first one. And the actual is going to be my H2 actual minus my H1. So from this point on, I could go about to finding this guy here, but it's actually easier if I just sub in this equation here for my Cp times delta T. From the bottom here, Cp delta T. Yeah, you guys remember that, hopefully. You guys remember that Cp is just the way that my enthalpy varies with my temperature, right? So this guy's always changing, but then since it says, oh, you guys can use the same one all the time. So that means that my delta H, okay, we can use the average one, delta T. Right, so I have a delta H here. I'm just going to sub that for Cp delta T. What's the question? What does the S stand for on S? Oh, so we use S because S is the letter that we use for entropy, right? So entropy, space to write it. We use S for entropy. So we just use S because we're reminding whoever is reading that this is the work for the isentropic one that doesn't change in entropy. So it doesn't really stand for a word per se. It's more of the meaning of the letter that we use for entropy. The CPs over here, they're the same, but the delta T's are going to be different, right? This is going to have, we're going to have the isentropic temperature here. Temperature one is the same. So I can go ahead and put, okay, if this is 80%, 0.8, right, efficiency, my delta T will be T2S, the ideal one, T1, divided by T2A for actual one minus T1. Okay, TS 585, T1 288, TA is the only unknown in this equation. So I can go ahead and solve for T2A, which will be T2A will be 288 plus 585.77 minus 288 divided by 0.8, which is 660.2. So indeed greater than the ideal one, as we expected, right? So it's not ideal, I guess I could say. It's quite trivial to say, but it's not ideal because it's actually going above what we would want from this compressor. Okay, so at this point, when we have this, what we can do is we can calculate the work for the compressor on the ideal case and the work from the compressor on the actual case. Okay, but we could go ahead and do that if we wanted to, but we don't have to, because not that we don't have to, but what I'm going to do before I do that is I'm going to find the same things for the expansion. I'm going to find exactly the same thing for the expansion. Now, let's talk about the expansion phase. Right, for the expansion, again, same relationship, right? T2 and T3s, but now for threes and fours. So my T4 over my T3 equals my P4 over my P3 of K minus 1 over K. So my T4, which is the thing that changes, the T3 does not change ever. It's going to be my T3 over my P4 over P3, K minus 1, K. K is 1.4, T3 is 873. What is P4 over P3? And watch out because it's a tricky question.
1/12.
1/12, right? Watch out because a lot of you guys like to put a 12 there. And you're going to get something that's absurd, right? It's 1/12. Why? Because P3, oh, here. 3/T4 is 12. So 4/3 is 1/12. Okay, so that's going to be 873, 1/12, 0.4, 1.4. T4 is 429.2 Kelvin. This is the reversible one, yeah? This is if it's 100% reversible. Same thing occurs, right? We're going from 3 to 4. So the lowest I can get on 4, lowest temperature I can go from here to here, right? The further drop I can have, the more work I'm going to get out. So when I actually look at the actual one, what I would expect is that for this temperature here to be higher. It's going to be higher, so I'm not going to be able to extract as much energy as I would otherwise, right? So let's have a look on the actual one. How am I for space? I don't have much space on the right side, so just do this. So let's have a look at the actual one. Like before, right? My efficiency is going to be the actual over the TS, so that means it's 0.8 will be, what is my actual? It's going to be CP, T3 minus T4 actual, divided by CP, 3 minus T4 ideal. CP's go away, and then T3 we have 873, T4 actual we don't, which is what we're looking for, and T4S we do, which is 429. So therefore, 0.8 times 873 minus 429.2 will be equal to, I'll put the equal on the bottom here, okay? So that my page is not being cut. But this guy equals C3 minus T4. And therefore, T4 actual equals 517.9. Indeed, this guy is greater than this, right? So we won't be able to extract as much energy out of the actual turbine as we would be from the reversible one. Lads, screenshot time, about to change. About to change pages, so go ahead. And I'll make sure to rewrite my T2, T2A, T4, and T4A on the other page. T2, T2A, T4, T4A. $660.2. All right, if you guys recall, what we're looking for is the backwork ratio, which is just the ratio between the compressor and the turbine. Okay, so let's go ahead and calculate the work now. Let's go ahead and calculate the work for the things that we have. So let's start with the compressor, since we did the compressor first. Compressor. So let's do the theory work of the compressor. So WS of the compressor, that will be my H2S minus my H1 which is the same thing as Cp of my T2, or T2s minus T1, right? And the one for my actual, what's that going to be? Well, my work for my actual, so to compressor actual, CA, is 2 actual minus H1 actual, H1, which is Cp, T2 actual minus T1. Cp, as I said in the beginning, is 1.005 kilojoules per kilogram Kelvin. So we're going to multiply by the Kelvin here, which is this difference here, and I've got the theoretical one to be 299.3 kilojoules per kilogram. And the actual one is 446. Okay, so as expected, the actual one consumes way more energy than the theoretical one. Now let's go ahead and calculate the same thing for the turbine. The turbine, my theoretical one, my theory one, will be my H3 minus my H4 S, in which case that's going to be Cp of T3 minus 34S, or T4. Anyway. Okay, 0.05, T3 is, what was it, 873 minus S, which is 249. That gave me 374.1 kilojoules per kilogram. And my actual one, turbine actual, equals 3 minus H4A, which is Cp times T3 minus T4A, which will obviously be smaller, and it ends up being 356.8 kilojoules. Okay, now we have the work for both of them. Let's finish off this problem. What is the backwork ratio? So we have two cases, right? We have a case in which we have the theoretical turbine in the actual compressor, the 80% compressor, and a case in which we have the actual turbine and the theoretical compressor. So let's first do the one. Let's do the one in which we have 80% compressor. We have the 80% compressor. My backwork ratio will be, what's the work of the compressor? The actual compressor, 446. What is the one from my turbine? 374. 374. So right now I inverted it. It's the compressor over the turbine. I inverted it.
Sorry, so it is for the theoretical one.
Which one?
This 80% compressor.
What do you mean?
Like a let me.
We're trying to compare. We're trying to compare one situation in which we have an 80% a compressor that works at 80%, which is this one here, and an ideal turbine. Right, so we're comparing these two guys here, and we're comparing that against one that has an ideal compressor and an actual turbine.
All right, cool.
Yeah, so it's actual over the turbine. Let me just make sure I get this right, the right values here. All right, for the compressor, that's going to be 374 divided by my turbine, which is 446, and that will be 83.87%. Okay, so now let's compare against the other one. Let's see what's the backwork ratio of one in which the turbine is 80% efficient and the compressor is nice and neat. So backwork ratio, what's that going to be? That's going to be the 2,993 divided by the 356.8. Okay, so actually have exactly the same effect, right? So the question was asking us which will have the greatest impact on the backwork ratio? A compressor with 80% efficiency, that's this one here, or a turbine with 80% isentropic efficiency? And the answer for that question is they both have the same impact, right? They both have exactly the same impact. Ratio. Hopefully you guys learned that.